Let me, let me begin by saying a couple words about the next homework. So in the first one, we're going to learn what some of these words are today. Consider the field extension Q inside QX, where that's really rational functions of Q. Show that QX squared is a closed intermediate extension. So QX squared is between Q and QX, right? Rational functions in X, rational functions in X squared. QX squared is a closed intermediate extension, but QX cubed is not. I'll define what this is today. Let K and F be an extension of fields such that the degree of the extension is 2. So there's an important lesson in this one. If the characteristic of K is not 2 and the degree of the extension is 2, then F is always Galois over K. We're going to get to the formal definition of that, but what that means, an extension is Galois if any element in F that's not in K can be moved by some automorphism of that. Give an example of a field extension of degree 2 over F, where the characteristic is 2 and F is not Galois over K. And give an example of a field extension such that the degree is 2 and characteristic 2 and F is Galois. So in the characteristic 2 case, sometimes an extension of degree 2 is Galois and sometimes it's not. And finally, final question is to prove or give an example to transitivity of Galois extensions. If E is Galois over K and F is Galois over E, is it true that F is Galois over K? Prove this or give a counterexample. Unfortunately, with this one, there's some words that we won't know until later today, but that's kind of cool. I don't think this one's too bad, but it's kind of a good warm up to familiarize yourself with these concepts. Okay. All right, let's kind of pick up where we left off. Okay, these are the set of automorphisms of F that fix F. I know one of those. This is just the identity automorphism, right? So the Galois group of F over F is trivial. How about this? Actually, let me. Here's our alpha and omega again. We did this example kind of in painstaking detail last time. This is isomorphic to S3. Right, there was 6 automorphisms. Flush things around. What is the Galois group? This. Where here again, omega. Well, you're asking yourself this, hey, self, what are the automorphisms of Q omega that fix Q? Would everybody agree this polynomial is irreducible over Q? Okay, so how many roots do we got? We got two roots and they're different, right? Omega and omega bar, right? Well, notice that Q omega is isomorphic to this, but this other root also isomorphic to this. Anybody want to venture a guess here? See, and these automorphisms, this is actually a degree two extension because the polynomial is irreducible to degree two. And this is induced by taking the root of that polynomial to the other root. That is correct. Yes, sir. How about this one? Add this on this?
It's the identity.
You are correct. Why?
Because the other two roots, would be complex.
Complex and not real, right?
Yeah, and we can't send them, we can't send this to either of those.
That's right. Once you understand where cube root of two goes, that determines the automorphism, right? Because this is generated by this single element. So once I tell cube root of two, you're going here, that tells you where everything's going, right? Where can cube root of two go? It can only go to another root of x cubed minus two. But the only root of x cubed minus two in that field is cube root of two itself. So here's what God is telling us. Everything in cube goes to itself, cube root of two goes to itself. It's the identity. Okay. Let me introduce you to some notation here. Well, this accounts this is theorem. 8 point something. 6. Let K and E and F be fields and H is subgroup Galois. So I have K and E and F fields. And H is a subgroup. The Galois group. Of F. Right. A. So like I said, this theorem also is introducing us to a little bit of notation. H prime, so this is a group. H prime is a field. It's the set of everything in F, such that sigma V is V for all H in H. Also. So I define this to be everything in the field that is left alone by everything in the subgroup of the Galois group. And this is an intermediate. Between A, F. B. E prime Well, E is a field, it's an intermediate field, E prime is a group. This is all the stuff in the Galois group of F over K. Such that sigma B is B. Oops, yeah, I didn't know this, but this is more suggestive. E of E equals E for all E in the middle. Is a subgroup of Galois. In fact, there's another name for E prime. Being characterized. It's all the automorphisms of F that leave E alone. So this is actually the Galois group of F over E. Right, it's a set of automorphisms of F that freeze E, if you will. Let's sketch the proof of this at least. And I go through this because I think it'll help us gain a little bit of familiarity with this notation. We need to show that this is an intermediate field between F and K. First note, if D1 and D2 are in H prime, then sigma D1, D1, and sigma D2 is D2 for all sigma and H. Therefore, sigma V1 V2 is V1 plus V2, and sigma V1 times V2 is sigma V1 sigma V2 equals V1 V2. So we did get that. So in other words, this set, whatever it is closed under addition and multiplication. Also, of course, that was clear. And so this is actually a field. Notice that H prime is contained in F by definition, right? Because here, and it contains K because H is contained in the Galois group of F of K. That means that everything in H fixes K in the first place. So it satisfies this. Everybody okay? How about E prime? Now suppose, let's say sigma 1 and sigma 2 are in E prime. This means that sigma I E equals E, all E and E. To show this is a subgroup, we just need to show that sigma one, sigma two inverse is in E prime. Oh, and I guess I'm using the subgroup criteria. Technically, I need this to be a non-empty set, but of course, what's one thing that's in E prime for sure? The identity automorphism. So when we're discussing E prime, we're not talking about an empty set. So, since sigma two E is equal to E, then sigma two inverse sigma two E equals sigma two inverse E. So sigma two inverse E is equal to E. So in other words, the inverse of the automorphism is in the automorphism. Hence, for all E and E, sigma one, sigma two inverse E is sigma one, sigma two inverse E equals sigma one equals E. So E prime is a subgroup of the Galois. Okay. Let me make number of remarks. Sometimes H prime is called fixed field. H and F. That is the subfield of F that's fixed by all the automorphisms that happen to live in H. Let me also make an observation here. What is one prime? Okay, and of course, by one, I mean the identity automorphism. One prime is all the stuff in F that is fixed by all the things in one. Just one. So this is all of F, isn't it? What happens when you prime this? Is not necessarily K. So what is this? This is everything in F that is fixed by the Galois group of F over K, right? This is at least K, because everything in the Galois group automatically fixes K. But maybe more stuff. So for example, does anybody have a concrete example? We've actually seen. The Galois group of this over this was the identity, right? So if you look at everything in this field that's fixed by everything in the Galois group, this is actually all of Q root 2, which of course strictly contains Q. So even though one prime is the whole field, it's not necessarily true that the whole Galois group of F, when you prime that, it doesn't necessarily go all the way down to K. It actually might be a little bit bigger. And this brings us to the definition of Galois. let K and F be fields. We say F is Galois over K. If the fixed field of the Galois group of F over K is precisely K. And I'm going to give you an equivalent way to state this that I've always found sort of computationally useful, if you will. Another way to look at this F is Galois over K. If for all alpha in F not K, there exists sigma in the Galois group of F over K that moves out. Sigma alpha is not equal to alpha. So think about what it needs to be Galois is if you look at the field consisting of stuff that is fixed by every automorphism, it's only K, right? This means that everything outside of K has to be moved by some automorphism, at least one. So that's why this is equivalent. And this is usually kind of, like I said, I find this computationally useful. So let's look back at these fields here. I'm gonna go back to our easy here. On the corresponding lattices. Corresponding. Let's go back to this example here. And let me, I don't recall, I might have these two swapped with respect to this, but I know I've got the other one right. But what these are actually, I should probably be a good way to look this up here. This is going to take real long to tell. P12 fixes, well, P13 fixes omega alpha. So that's what I did first. P13 fixes omega alpha, so let me do that. Okay, now this is right. So the corresponding pictures here, what happens here, of course, this is three. And same business here. Oh, wait, two, 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 three, two. Right. Notice that we've seen from examples here. This thing is not Galois for this. And it's easy also to see that these two are not Galois for Q as well. Right? But if you look at this one here, we also saw this example. This one is Galois. The difference here is normality, right? It turns out that this thing is Galois over every intermediate extension, right? This one is Galois over this, it's Galois over this, this, and this. Okay? But the intermediate extensions, this one is Galois over this, these three are not Galois. So that kind of, you might go through and check that, but it's easy to verify. Now, I am going to break down and do it. I'm going to give you the fundamental theorem of Galois theory. And it's basically a bunch of words that mirror exactly what these pictures here say. And the rest of a little while, it'll probably take a couple days, we're going to develop some machinery and give a more or less complete proof of this. But without ado, let's get the statement here. So this theorem, 829. Fundamental theorem. Let K and F be finite in Galois. When I say finite, I don't mean the fields are finite, I mean the extension is finite. This is finite degree. By the way, does anybody remember what we know about a finite extension? It's algebraic, right? So we've automatically got that F is algebraic over K, or algebraic over K. Then there's a one-to-one correspondence. A one-to-one correspondence. Between intermediate fields of the extension K and F, and the set of subgroups of the Galois group. And this is given by I'll tell you exactly how the correspondence works. Here is an intermediate extension. And this goes to E prime, which is the Galois group F over E, as we had pointed out, such that A if L and M are intermediate fields, Tell them are intermediate fields, then so the degree of the extension of M over L is equal to the index of L prime and M prime. So notice this is a degree of a field extension, and this is an index of, right, this is an index of M and L. So in particular, from this follows the order of the Galois group is equal to the extension. And P F is Galois. So remember, our basic assumption is that F is Galois over K. F is also Galois over every intermediate extension. So Galois over the base field K means it's Galois over every intermediate extension, but the intermediate extensions may not be Galois over the base field. But E is Galois over K if and only if the Galois group of F over E which is C prime, is a normal subgroup of the Galois group of F. And in this case, what happens when you have a normal subgroup? You can mod out by it, right? So what happens when you mod out Galois group of F over K, modulo the Galois group of F over E is isomorphic to Galois group of E. So for example, if I look back at this example that I beat to death here, this example illustrates this nicely. In this case, this group is normal in oops. This is normal in S3, right? And what this says is if you take the Galois group of F over K, which in this case is S3, and you mod out by the Galois group of F over E, which in this case is E prime, which is Z3 or A3, right? This is isomorphic to the Galois group of this over this, which is actually Z2. Okay, any questions? So this is basically, this tells you, this picture tells you pretty much everything going on about it. The correspondence here, E goes to the fixed field of this. If you remember from our example, this was the real, this is Q adjoining alpha, the real Q free. And we saw from our table that the fixed field of this, or I'm sorry, the E prime, this is the set of automorphisms of all of F. Fix, the real part was just this automorphism, which was, this one was essentially complex conjugation. So complex conjugation is the only thing. So this is how the correspondence works. Field goes to the automorphisms that fix it. And we have the intermediate fields. Here you can see my numbers here pair up. This is the contained here, and we've seen this as well. So any questions on what the theorem says? Now that we've done what the theorem says, we'll pop the hood. We're gonna the engine. Okay. So let me give you the following limit. This is full of little bits that are interesting in their own right. Not too difficult to prove most of them. Limit 8 to 10. But here's a bunch of factoids that we're going to need here. The statements of these, I've got a bigger setup here than the statement. Let K and F be Galois with intermediate fields of L and M. Galois over K. With L, intermediate fields. Let G be the Galois group of F over K and H and N be subgroups. H and N are subgroups of G. The following conditions hold. Number one. Number one, F prime equals 1 and K prime equals 3. Here, my prime notation is what I introduced earlier. B, 1 prime equals F. We've already made this observation. C, if L is an M, this implies that M prime is a subgroup of L prime. So in other words, the containment reverses itself. If H is a subgroup of N, this is a subgroup of N, then you get the reverse containment on the fields. M prime is contained in H prime. E L is contained in L double prime. And H is contained in H double prime. L prime is L triple prime. These kinds of notions like this, it's always seems to work out. And H equals, or H prime is H triple prime. Right. And that's what we have to go once. Um. Let me kind of talk you through, we've already discussed B. For A, F prime is one. So let's see, what is F prime? This is the set of every element of the Galois group of F over K that, right, that fixes all of F, right? And if it fixes all of F, it has to be one, right? So there's that. K prime is a set of every automorphism that fixes K. Well, that's everything in the Galois group by definition, right? So there's really nothing. The first bit is just about what the definition is, really. Let's look at C. Let us suppose first that right. Suppose that sigma is in M prime. So what does this mean? That for all M, sigma M, two, right? But since L is contained in M, sigma L equals L, right? So L is a subfield here. Therefore, sigma is in L prime. So we have M prime is contained in L prime. Right? D is very similar, although I seem to have become dyslexic. So let's look at D. Let's see, we've got H and N. So let's let N be an N prime. I remember N prime is a field, right? So sigma N equals N for all sigma and N. So sigma N is equal to N for all sigma and N. And of course, sigma and N contains H. Therefore, sigma N equals N for all sigma and H as well. And therefore, N is in as okay, let's see, where are we at now? E, we need to show that L is contained in L level prime. So for this one here, there's this problem. For this one right here, I guess I'm going to put down. I want to just be careful about my definition set. So notice that L prime. So we start with L being a field. L prime is the set of sigma and G. Such as sigma L is equal to L. And So if L is an L, then sigma L is equal to L. For all sigma and L prime. Because this is the way that L prime is actually constructed by our definition. And so by definition, L is an L double prime. Because now L prime is a group and its prime. This is a group. Its prime is everything that is fixed by everything in L prime. And by definition, it's that. Hence, we have that L is contained in L. I think that that is a good place to finish. We'll tidy this up some more next time. Any questions? I encourage you all to consider the math club today. We've got a visitor in. It's on model theory. Should be really kind of cool stuff. Hope to see you there. Otherwise, you all have a good weekend and we'll see you on Monday.